Today, in Lesson 2 of Functions and Relations, what I want you to be thinking about are I can statements that I can explain and apply the definitions of functions. We're now going to put on a video that I'll have you watch, so listen carefully and we should be able to fill in some of these notes.
There's a type of relation that's going to be much more useful than the others. It's a special relation called a function. The definition of a function and what makes it special is every element in the domain is paired with a unique element in the range. In other words, every element in the domain gets only one element in the range. Saying that another way, every x is paired with only one y. If you still have trouble, we say, as long as all the x's are different, okay? The deal is that there's going to be some sort of a formula, typically, in a relation that maps every x to y. That gives every input variable x an answer y. Now, if any of those x's have more than one answer, well, it's not going to make it a very useful formula because you won't know which answer to use. So we're going to limit our practical relations to functions. And these are the ones that, if you would, have only one answer. Or, as I said, every element in the domain, the x's, is paired with only one element in the range, the y's. Let's look at some examples. For instance, relation A is every x mapped to only one y? Or are all the x's different? And some of them they are. All the x's, 4, 0, 6, and 2, they are all different. Now, two of them are mapped to the number 6. 4 is mapped to 6, and 2 is mapped to 6. But each of those elements, 4 and 2, is only mapped to one number. So as long as it's only mapped to one number, in other words, each x only has one answer, then you do have a function. So, relation A gets the function seal of approval. Now, let's look at relation B. All the x's are different. That's probably the easiest way to do it, isn't it? No x is paired with more than one y. So once again, we have a function here, a relation that is a special type of function, a special type of relation, a function. In C, all the x's are not different. In fact, in this case, they're really not different. They're all the same. The number 1 gets mapped to various answers. 1 gets mapped to 4, 1 gets mapped to 3. And it only takes one repeat to mess it up. So this, while this is a relation, it is not a function. Finally, D, this is a little bit confusing. D is a relation that has all the x's are different. 4, 3, 2, and 5. They're all different. Now, they all get mapped to the same number, but they don't get mapped to, and no one gets mapped to more than one y. So, believe it or not, relation D is in fact a function. Note once again, the y's do not have to be different. It's the x's that have to be different. Not fair, isn't it? But that's the way it works. Every x gets only one y, or every input has only one answer, if you would. Now, consider that these pairings can actually be xy points. If we look at the picture of a relation, we can test whether that relation is a function graphically. We can test visually whether each x has more than one y by using what we call the vertical line test. If we run a vertical line test across the graph and it never touches more than one point at one time, in other words, if we move a vertical line across the graph without hitting that actual green graph in two places ever, then, and you see, then in fact, we do have a function, and in this case, we do have a picture of a function. No x got mapped with more than one y. It is a function. Let's see if this relation is a function using the vertical line test. It went a little quickly, but it never hit 2 at the same time. So that function is, or that relation is a function. Now just when you thought all relations were functions, let's take a look at this one and see what would make something not be a function. There, in that spot, it actually hit, okay, you see, 2 points for the same x value. That's the x value 2, and 2, hopefully you can see, got mapped to about 1 and about 5. So 2 got mapped to 2 things, and of course the vertical line hit the picture in 2 places at the same time. So while this is a relation, it's not a function. How about this relation? Well, does it ever hit the green line in 2 spots at the same time? It doesn't, so that it is a function. There's something screwy around here. Now this relation, if we use the vertical line test, hits it in 2 places at that spot. And it only takes 1 double touch to mess it up. Now there are many other double touches here, aren't there? But it only takes 1 to mess it up. So while this may be a picture of a relation, it is not a picture of a function. You recognize this relation? Maybe you don't, but this is a picture of the sine function. Why do you think it's called the sine function? Because it is, in fact, a function. No x gets mapped to more than one y. Once again, I need you to remember that a function is a special type of relation where every x gets mapped to only one y. So every input that you put into maybe some formula, that formula is such that it only comes out with one answer for each of the x's. So,
Alright, so from watching that, what we want to look at is in your notes. We want to try and fill in your notes. As you are filling in your notes, we want to say a relation is a set of input, and what we are looking at is output pairs. A function is a special type of relation. And when we look at that relation in a function, every input should have, if we are looking at this, exactly one output. Your domain is the list of all possible inputs. This is really all the x values a lot of times that we're talking about. Your x values in your table, an input. The range is going to be our list of output values. So when we are looking at that, we are talking about our outputs. So this is going to be our outputs that we are looking at. And again, we might think of this as our y values when we look at those. In problem 1, what we want to take a look at is tell whether the relation is a function, and we have to explain. And the explanation is usually something like for each input there is one output, something along that line. So we're going to look at this first one. We look at our inputs, and again, just like in the video, we want to see, do we have all different x values? Whoa, right here. Okay, 4 has 7 and 4 has -5. So is this one a function? Our answer is going to be no. Why? Notice also 2 and 2 again. So both 2 and 4 have 2 outputs. And really remember what they said in the video, you need only one to not work. If we look at this next one, we have -1, 0, 1, and 2. All different inputs, all different x values. The output is our y value. And as we look at those, even though 1 goes to -1 and 2 goes to 1, this one is a function. And we're going to say, yes, it's a function. Each input, that's going to be our reason. You're going to use this reason a lot on your homework. Each input has one output. Again, we're going to look at all of our x values first. -5, -4, -3, -2. Each input has a unique output. So yes, this is a function. Again, y. Each input has one output. I would like you to try the last one. You're going to put down in your notes. So when I check your notes tomorrow, I will see that you've told me, yes, it's a function, or no, it's not. Think about what we've talked about and what was in the video. The next thing we're going to do is write function rules. And if you remember in our last unit as we were writing equations, we were always looking at our input and our y being the output. This is our change in y. Remember that, change in y. Here is our change in x. What did we say the slope was? The slope was equal to the change in y divided by our change in x. In our equation, if we're looking at this table, the change in y is equal to 2 divided by the change in x, which is also equal to 2, and it gives us a slope of 1. It says, what is our y-intercept? Well, notice there is no y value here of x, or x value of equaling 0. But if we notice this is going by 1s, if this is -4, we should be looking at -3. So if we are looking at that, our y-intercept would be -3. Remember, in a table, it's when x equals 0, it is the y value from our last unit. So now our equation. Again, think of slope-intercept form. Y equals, in this case, 1x minus 3. So for every x value you plug in, and you can check, plugging in x is 1, 1 minus 3 gives us -2. Plugging in 3, 3 minus 3 gives us 0. The next one, you're going to read the situation. You have $16 to spend at the arcade. You want to spend $4 on food. Each game costs 50 cents. So each game, and we're looking at how many games. So X is our games, if we're thinking of, that's what we want to know how many, and Y is our dollars that we're spending. So what is our function? Well, how much does each game cost? 50 cents. So 0.5 or 50 X. But we've spent $4 on food already, so we don't have the total 16 to spend. We've already spent 4 on food, which means at 0, if we're looking at games that we can play, remember at 0 we've already spent our $4. Remember, this is our dollars, and then our games are X. If we look at that, we now want to figure out for 8 games. Well, follow your equation. 0.5 times 8, half of 8, plus 4. That means this is 4 plus 4. Gives us $8 spent. I would like you to figure out, look at the 16.5 times 16 plus 4. I'm going to pause the video. I'd like you to pause the video in class today and figure in those last two, and then we'll start it up. Unpausing the video, you should see that you got 12 and 16. So how many games can you play for $16? We can play 24. The next question asks us to look at the domain and range. And as we look at the domain and range of this, the domain is what values can we use for input. So when we're looking at the values we can use for our input, we're talking about 0 to 24. Those are the number of games that you can play when you go to this arcade. And the range is 0 to 16, and that's the dollars that we have. Right now, what we are going to do is make this table of inputs. And you're going to see this on the next video, and then I'll explain a little about the homework also.